I appreciate Noble Foundation giving me the opportunity to be here tonight, and if you have some questions, go ahead and ask them as I'm going through the presentation, and I'll try to answer them, but Eddie told me I got 40 minutes, and so I talk real fast sometimes, so hang on and let's see what we can get through here. So first of all, what I want to try to do is discuss the drilling fluids from a standpoint of what they are, give you a little bit of idea of some of their properties, and then discuss some of the soil and drilling fluid analysis that we would suggest producers do before they ever have any inkling that they're going to allow this to be put on their land. What are some of the pros and cons for land application of these materials? And then are there any kind of groundwater potential issues that we might see? Chad Penn, Dr. Chad Penn is a researcher at Oklahoma State and has given a presentation a couple of times across the state with some good information related mainly just to Oklahoma. And so what I did is I borrowed some of his slides, and so this first part's going to be most of the information that has come from Chad. So question first of all is what's land application? And this is where soil scientists and regulatory agencies sometimes have some different opinions as to what land application really happens to be. So often used synonymously with terms of soil farming and land farming. It's technically, really and truly, land application is neither one of those. And so what we're trying to do from a land application standpoint is provide at least some type of beneficial use of that material in recycling. At least not be detrimental to the soil. That's the key. Drilling muds are coming from oil and gas exploration. Some of the things that those materials are used for is, first of all, to seal the formation, remove any of the cuttings that are coming out of the hole, lubricate, cool the drill bit, control any kind of corrosion that might be around the drill stem, and then control well-borne pressure. Operators adjust their recipe depending on what the depth happens to be or what geologic material they may be going through so that they can drill through those types of materials. So this is just kind of a schematic. I'm not going to go over that with you, but they recycle that mud as many times as they can in order to, first of all, use the least amount of mud that they can, but also get all the use out of it that they possibly can so that they don't have so much material to actually have to deal with. So what is the drilling mud? There's lots of different things that go into it. Again, each driller is going to have kind of their own recipe that they use. But most of them are going to contain at least parts of these materials. Bentonite clay, which is a shrinking swelling clay, and there's a few places here in Oklahoma where you have those shrinking swelling clays naturally. But this is usually used to seal ponds, for instance, from an agriculture standpoint. Barium sulfate, this is a very heavy compound, and so it adds a weight material. Lime, which helps to, from a corrosion standpoint. Soda ash, which is sodium carbonate, and this is a water conditioner. Lignite, from a viscosity standpoint, and then some sealers that are used to maintain that circulation of the material. And those kinds of things could be ground peanut shells, mica, cellophane, walnut shells, lots of different types of materials that they would put in there to help keep from losing that circulation. There's two types of materials that we deal with. One is the water-based and the other one's the oil-based. The water-based is the one that is more often applied as compared to the oil-based, and primarily because the oil-based there's only a certain amount of oil that can be applied. At least we have that regulation in Texas, and so most of the time we don't see very much of the oil-based materials applied, but we do see the water-based materials applied to the land. Very different characteristics, again, like I said, one mainly from an oil standpoint and the other one's mainly from a water. Contents of the two different things. So this is a water-based. It's got a lot of what we call dissolved solids. It's got a lot of sodium in it, and sodium is one of the major problems that we have with this produced water. And the primary reason that we have the problem with the sodium is because what happens whenever we get a certain amount of that into the soil, it has a tendency to disperse the soil. And once we get dispersion of the clay particles and the organic matter, then that seals the pore space that we have in the soil. And so instead of having the ability to get water into the soil, that first little bit of precipitation seals all that pore space, and water doesn't have any place to go, so we get runoff. So we distribute that material more across the landscape, and we also cause erosion. So it's a big problem. And so that plus the chloride. There are a lot of plants that are pretty sensitive to chlorides, as low as concentration as 250 parts per million. And then there's some others that are very, very resilient to chloride and can go up to almost 5,000 parts per million. So it kind of depends on what your vegetation is that you're trying to grow in that particular location. The bentonite really doesn't cause any problems. Most of the time, it doesn't have a whole lot. It doesn't have a whole lot of nutrients in it. But what it does is it adds to a process that we call cation exchange capacity in the soil. And what that does is it gives the soil a better buffer capacity. So it adds clay to the soil, and so that's usually a good thing if you've got a sandy soil. But if you already have a clayey soil, you don't need any more clay. So again, it's one of those decisions that you'll need to make. And then, of course, water. Typical contents of the oil are going to, again, it's going to have a lot more petroleum, hydrocarbons to it. It's going to have, it's not going to have as many dissolved solids as the water-based does. Calcium carbonate equivalents, which means it has a liming capability from a soil. So if you have acid soils and you need some limestone, this can give you a little bit of calcium carbonate equivalents and raise your pH a little bit. The minerals that we see that it's usually fairly rich in is calcium, magnesium, and potassium. And again, it depends basically on the geologic material that it's coming from and what it's being drilled through. Water-based, like I said, the biggest problem that we got with it is the salts. Both the chloride and the sodium can give us problems. At least in Texas, they don't analyze for sodium. That's not one of the requirements that our Railroad Commission makes them do. They make them do chlorides and salt content, but they don't make them do sodium, and we've been trying to get them to make for sure that that's an analysis that they do. If you've got excess sodium, again, you get the poor drainage. You get very little structure in those soils as well. And so without the structure and without the drainage, then you get big problems from the standpoint of erosion. Now, one of the things that we use to treat that with is gypsum. And then once you get the gypsum, which is calcium sulfate, you add that to the soil, then what happens is the calcium replaces the sodium. We reestablish that drainage capacity because we no longer have that dispersion of the clay particles. And so we open it back up as far as the pore space is concerned, so we can get water to move through it. And based on getting the water moving through it, then we can actually get the salts moved out. So you have to do the gypsum first. You can't start trying to add the water because, again, the water won't go into those soils. TPH, total petroleum hydrocarbons, is toxic to plants if you get it up to a certain point. And so this is not typically a long-term risk, and the primary reason for that is because that material is degraded by the microorganisms in the soil fairly quickly. So you may get a vegetation kill for a short period of time, but it doesn't take very long, and actually most of those areas will recover very well if it's just an oil spill. Again, the salinization and the sodicity is not as much of a risk with the oil material as it is with the water-based materials. There is a radioactive risk on any of these materials, and the primary reason for that is just because we're drilling through geologic material that have a certain amount of radioactivity. And so this, if you happen to be using drill stem for your fences, for instance, you're going to have some radioactivity in that drill stem. And so that's one thing that you need to think about too. If you're using a drill stem that's been used and they're no longer using it, there's going to be a certain amount of radioactivity associated with that drill stem as well. We've got a threshold. I think Texas sets a threshold of 20. Oklahoma's threshold is 30 picocuries per gram. The bricks on this building have a higher radioactivity than that, so it's actually pretty safe concentration. Just briefly, this is what you would be doing from a land application standpoint. Maximum slope, you want it to be less than 8%. And this is a spot where we really start to see quite a bit of erosion whenever you get past about an 8% slope. So that's the reason for that particular threshold. At least 12 inches of acceptable soil from a good texture standpoint. Must maintain the buffer zones, whatever that happens to be. There's a certain distance that they require on each of the different types of locations, ponds, water, any kind of stream. Electrical conductivity, that's what the EC stands for, of less than 4,000 microsiemens per meter, and an exchangeable sodium percentage of less than 10. Now, the exchangeable sodium percentage goes back to what I was talking about as far as the sodium's concerned. So once we get more than 10% on those exchange sites that I was talking about, then we start to see this dispersion of the soil, and we have problems with the soil plugging. The 4,000 microsiemens per meter is would be the same as if you send in a soil test and they do it in millimoles per centimeter, then that would be 4. So what does that mean, or where do we get that number, and who cares about it? Well, at that point, we start to see a lot of crops that are fairly susceptible to salt damage having problems. We can have some issues lower than that, but at 4, there's a lot of crops that are going to, or at 4,000, there's a lot of crops that are going to have some issues at that point. And so that's a point where we set that. That also dictates where a soil is considered to be saline. Depth to bedrock, 20 inches for water-based material, 40 inches if it's oil-based material. No water table within the top 6 inches of the top 6 feet, of the soil profile. Water-based materials can be respread after 3 years has passed and the soil test requirements are met. Texas, it's a one-time operation, or it's considered a land or a landfill as compared to our farming operation. As compared to just the one-time application. The oil-based materials sites cannot be reused for either the water-based or the oil-based materials. Loading, based on the commission's corporation commission, cannot exceed the following things: 6,000 pounds per acre of total dissolved solids. This goes back to the amount of salts that you have. 3,500 pounds per acre of chloride. If you convert that to parts per million, that's 1,750. Total petroleum hydrocarbon, 40,000 pounds per acre. And then on a dry weight basis, as far as the amount of solids that can be applied, 200,000 pounds per acre. Okay, how many tons is that? 100 tons. Okay. Okay, so that's a lot of material. Based on my guess would be that would be somewhere on the order of 2 to 3 inches thick. Handling of the mud, the oil-based material is spread only as a solid, and it's got to be mixed with some kind of bulking agent. This may be some straws or something like that. 3 parts to 1 part of the oil-based material. And then the water-based material is typically going to be, or it can be applied either as the liquid or it can be applied as a solid. Keys for the producers. The more available acres, the better. The thinner you can spread this, the better off you are. Okay. Check the reputation of the spreading contractors. You can call the Oklahoma Commission and find out if they've had any complaints. And being in Texas, there's some companies that are doing a good job, and there's some companies that are not doing a good job. And so more than likely, you probably already know the ones that are doing a good job and the ones that aren't doing a good job, because it doesn't take long from a word of mouth standpoint to get that kind of information spread around. Good contractors will work with you from the very beginning to the end, and I usually tell producers that beginning to end is not from the time that they start applying it until they finish applying it. It's 3 or 4 years down the road, so that you can see if you can get whatever your crop was to grow at the yield goal that should have been growing there. Cannot be used on CRP ground. Everybody knows what CRP is, Conservation Reserve Program? Okay. Ask questions. Always ask questions. Problems do arise. By rule, bona fide effort must be made to reestablish that vegetation. Properties, this gets into some of the information that we supply as far as our producers are concerned. Again, just to give you a little bit more information on these, they're going to have that high electrical conductivity. They're going to have a lot of salts in there. Sodium content, chloride, barium, sulfate. Now, sulfate's not usually a problem for us, thank goodness. But if it does get in our water, especially our surface water bodies, then we have some issues because it serves as a very good laxative. And so if you've got animals drinking water where this material's running off of and into a tank, you could have some issues there. The bentonite clay even the water-based material is going to contain a little bit of oil and grease. And so you need to get know that kind of information as well. And it does have some certain metals in it. Now, there's not any metal regulations for this material, but there are some other rules and regulations that we rely on in Texas to look at those metals. And I'll get to that in just a little bit. So total salts, what are some analysis that you need to be doing in order to make for sure that you can make a good decision? And that's what these are the ones that I'm going to cover now. So first of all, you want to know what the total salts are. The majority of these tests are fairly cheap until you get to the metals, and then they can start costing you some money. But most of these other tests are fairly cheap. The total salts, again, is measured as the electrical conductivity, and there's lots of different ways that they'll report it to you, but most of the time, if you ask for total salts, it'll be reported to you in parts per million. Just gave an example here. You've got an electrical conductivity reading of 0.38. That's millimoles per centimeter. In the table, or in the previous information, I showed you 4,000. Well, that 4,000, if I put it in these same units, would be 4, so that you know what units are going on here. So we take that, multiply it by 640, and it gives us an estimation of the amount of salts out there in parts per million. You can take parts per million in most things, and you can multiply it by 2, and that gives you pounds per acre. Any questions on that? Now, some information from a standpoint of the conductivity. Where does it start to play a role? Well, if you take a look at this is just for water, okay, but it gives you a good idea of materials that you're going to be applying, especially since this is a water-based material. We don't have much problem until we get about that 2,000 micromoles, or it would be 2 in millimoles. So once we start getting at that point, we're going to start seeing some issues. And whenever you get to 3,000, it should not be used. And that, again, that's from a water standpoint. So if it's being applied as a water or as a liquid, you want to take a look at that conductivity and see what it is. The extractable ions that we suggest that people take a look at are the ones that would be what we consider to be a routine analysis through the soil test laboratories, and then also boron and chloride, because those are not two that are typically done in most laboratories, or most soil testing laboratories for agronomic purposes anyway. So the reason for the boron is it is usually associated with any kind of salt issues, and of course the sodium and the chloride are going to be there from the drilling fluids anyway. The sodium adsorption ratio is a key, and that's what we look at from a standpoint to get an indication, or that's one thing that we take a look at to get an indication of the potential for having that sodium problem out in the field. The equation for that is the sodium divided by the square root of calcium plus magnesium divided by 2. So if you got an example of what I showed down here, the analysis that came back was sodium was 460, calcium was 200, magnesium was 120. You change those back to millimoles per liter, and we calculate an SAR of 20. And so let me show you those. So this is where we start to see the sodium hazard with when we're using sodium adsorption ratios. We're less than 10, we don't have much of an issue. But you start getting into this 10 to 18, and there's going to be some crops that you're going to have some problems growing. You get up past the 18, and you got big problems, because even at that point, you're going to start getting some dispersion of your soil. And then you got big problems from the standpoint of drainage. All this information separates out the four classifications that we have as saline and or sodic soils. And it's based on pH, electrical conductivity, and then the exchangeable sodium percentage. And what happens is when you get non-saline and non-sodic, you have pHs less than 8.4. You're going to have an electrical conductivity less than 4 millimoles, and you're going to have an exchangeable sodium percentage less than 15. If you're saline, then the conductivity goes up. So you're greater than 4. If you're sodic, the salinity doesn't necessarily go up. Okay, so you're less than 4 if it's non-saline but sodic, but your exchangeable sodium percentage goes up to over 15%, and the pH will go up over 8.4 or 8.5. When you've got them both, when you have both saline and sodic, then you have pHs less than 8.5, you have an electrical conductivity greater than 4, and you've got an exchangeable sodium percentage greater than 15. So that's how we separate those into the four classifications. So you've got to know which one of those you're dealing with if you allow this material to be applied to your land. Do you have just a salt problem? You can leach it and not have an issue. Do you have just a sodium problem? Then you've got to add the gypsum before you start messing with adding any water, because you can't get water in the soil. If you have both the saline and the sodic issue, the soil still drains. And so if you're out there and you're just looking at it and you think, well, soil's draining, so it can't be a sodium issue. Well, you go in there and you add water, and what happens is we wash the salts out and we leave the sodium behind. And now we've gone from a saline sodic soil to a non-saline sodic, and it seals. And so know the salt issue before you start trying to do something to remediate it. That's a key. And then the metals. These are the metals that we typically recommend: arsenic, barium, chromium, copper, lead, nickel, and zinc. And whenever you send these to a laboratory, they're going to be reported to you more than likely in milligram per kilogram. And this is totals. The others I've talked about have been what we call extractable. Okay? This is going to be based on total elemental analysis. Now, this information comes from what we call the 503 regulations. This deals with biosolids. But this is the best set of criteria that we have as far as metal analysis are concerned and metal loading rates are concerned. And so TCEQ stands for Texas Commission on Environmental Quality, so that is our corresponding agency to your Oklahoma Commission. So these are concentrations in the drill, what we suggest as far as in the metal, in the drilling fluid, that, and again, they go back to a regulation, but it's not, it has nothing to do with oil and gas. But these are the parameters that we are using to meet from standpoint that we're making recommendations for producers, because it's already a regulation, just not for this particular material. Once you get it land applied, then you've mixed it with the soil. And so then you've got another set of criteria to take a look at from a soil standpoint, and that's what these happen to be. So these are in pounds per acre. If you want to take a look at this, and if you get analysis on parts per million or milligram per kilogram, then you take those values and divide it by 2. And then you've got an estimate of the milligram per kilogram or part per million. Total petroleum hydrocarbons, less than 1%. This is not going to be detrimental to plant growth. I've seen a lot of plants growing in about this much oil and doing quite well. So the hydrocarbons don't cause us near as much issue as the salts do. It doesn't look very pretty, okay, if you got a lot of hydrocarbons out there, but from the standpoint of plants growing, a lot of times they'll grow pretty well in that material. But again, the salts is a major thing that we have from a cropping situation that causes the issues. We recommend for our producers, and your routine analysis through your soil testing laboratory at Oklahoma State is very similar to ours. They use the same extracting procedures that we do. And so you can go by that. Now, from a metal standpoint, we usually suggest that you send those out to a commercial laboratory that does environmental type soil analysis, because they follow the EPA methodology, and if you have to go to litigation, that's the way you're going to have to go, because those numbers are certified. Whereas a soil testing laboratory is not going to give you a certified number. So our routine analysis are electrical conductivity, pH, extractable nitrate, nitrogen. This is one that you do not do, but all the rest of them you do. And then phosphorus, potassium, calcium, magnesium, sodium, sulfur. Those are all done by Malik 3, same thing that Oklahoma uses. And our recommendations are very, very similar to what Oklahoma is for the same crop and yield goal. Copper, iron, manganese, and zinc we do by DTPA, and I'm pretty sure that that's the same analysis or method that Oklahoma State uses as well. Now these are extractable. So these are related back to what a plant needs. Those totals have nothing to do with what a plant needs, okay? Texture, you need to know the texture of your soil. Now, you could do that, you know, if you're good enough, you can go out there and make your, you know, your little cigar, roll at your little cigar and put it between your thumb and forefinger and get the texture. Or if you've got a soil scientist that's out there working with you, they can get close enough for you for that texture that you don't have to pay for it. But you do need to know what the texture is that you're starting with. And then I suggest you do the cation exchange capacity because, again, if you're adding that mud, it's going to change your cation exchange capacity, which is a good thing in sandy soils. It's not necessarily a good thing in your clayey soils. And the primary reason for that is you don't need any more clay, more than likely. Adding clay to clay is not necessarily a good thing to do. So in Texas, we have 3 different ways that they can land apply these materials. The first way is an agreement. This is basically a handshake. And this is between the landowner, of the well site, and it is for a one-time application. My suggestion is you get a lawyer and you make for sure that you have all the parameters down that you want done before that material is applied. You make a decision as to, based on that material that they have versus what your soil contains right now, how much can you apply and not cause detrimental effects. That's the key, okay? And you need a time period. You need to know, you've got to be able to look at multiple years of growth. If you just look at it this year, it might have been just the tilling process made a big difference. Okay? You could have a compacted pasture, and that tilling process broke your pasture up, got a renovation out of it. Okay? That's a good thing. But the next year you come back and nothing's growing, they've already walked away, you've signed the papers, everything's finished as far as they're concerned. Don't do that. Make for sure that you've got 3 or 4 years of growing time to make for sure that that was done properly. Registration, the second part, is that's off-site and it's a one-time application. And again, my suggestion is whoever has that land, okay, whoever's the landowner, make for sure that you've got a lawyer working with you to draw up the papers to make for sure that things are carried out properly. And then the last one that we have in Texas is a permit. This is for multiple applications, and this was what we would call land farming. Okay, these others are we would look at more as either to improve the soil tilth or something like that. But this would be multiple applications, and we would consider that a commercial site. So the Railroad Commission, this is for land farming, and again, most of us from a soil scientist and agronomist standpoint don't agree with terminology that's used in this case, but they are what they are. So this is for water-based. So their definition of land farming is a waste management procedure whereby freshwater-based drilling fluids are spread on the soil to regenerate the soil horizon. I like that. The ideal site would be flat, no trees, no natural drainage, with levees around the site. Site should be disked within 30 days of application. Okay, got a few things that I don't agree with on that one. Number one, it is not a regeneration of the soil. Okay, this material can be detrimental if it's not applied at the proper rates. Okay, and so it's not it does not regenerate soil. The other thing is that it's not a land farming. This is a recycling of materials. Yeah, but land farming is where you are putting a lot of material on there, and it's actually a commercial site where you're doing multiple applications and using it as a site just to dump those materials on. Wait until 30 days. you've got lots of opportunities, if it does rain, for that material to move off-site, okay? As soon as they get it applied, it needs to be incorporated, okay? So don't let it sit out there for 30 days. Site can be permitted only once. Fluids must be below 3,000 parts per million chloride. And again, at that point, there are some plants that are pretty tolerant to chlorides, and that will be okay. But if you're trying to grow something that's very sensitive to chloride, 250 parts per million is what you need to be looking at. Must have the pH between 6 and 10. We would prefer 6 and 8, and I know that's not going to be met. Levees must be erected around the proposed site. This is not happening. I don't know whether that's a requirement here in Oklahoma or not, but very seldom do we see the levees. Stormwater discharge is prohibited. Unloading may not be conducted during episodes of heavy rains. That just makes sense. Fluid is not to be applied thicker than 4 inches. Now, for most of y'all, probably you have watched materials grow before, and you planted seeds. Do you plant them 4 inches deep? If you do they ever come up? No. Okay. So 4 inches deep is way too deep. Okay. So we try to get them to apply no thicker than about 2, sometimes 3 inches, just depending on what that material might be. Most of our Bermuda grasses will come through 3 inches, but you put that fourth inch up there, and most of the time it's not going to come through, especially if it's a heavy clay, which is part of that material. Area must be disked within 30 days. Again, we want that to happen that day. Area must be generally flat. That's a good one. Wooded areas are prohibited. That's good. Verbal agreements between the operator, representative, and landowner does not relieve operator from complying with statewide Rule 8. The permits that are issued to the operator, and the operator's got to furnish that to the carrier. Okay. Generator is responsible for the proper land application. So it goes all the way back to the generator. Now, I don't know in Oklahoma, that y'all have to talk about that. Some of the pros, tilling can help, especially in compacted pastures. You get a renovation of your pasture. It adds some clays to sandy soils. And in doing that, you increase the cation exchange capacity, and in doing that, you also hold the nutrients better in those sandy soils. So it does some good things. Reuse is a waste, okay? That either goes to a landfill or we recycle it, okay? And so if we can recycle these materials, it is very beneficial from a global standpoint. But if it is not suitable for being recycled, we need to landfill them. Cons, it adds salts to the soil. And these are salts that are not required by the plant. Okay? Adds clays to clayier soils. Application over 3 inches is going to kill grass. Almost any other kind of vegetation is going to kill, so you got problems. And it really and truly contains very few nutrients that the plant would actually take up. Now, there's some research being done here at Oklahoma State, and they are showing some increases in yield where these materials are applied properly. Okay? So Chad Penn is doing that work, and so whenever that, he's hoping that at least some of that's going to start coming out at the end of this year, possibly in the first of next year. So watch for those kinds of publications. Now, this is what it can look like if they don't do it properly. Can it be regenerated? Can it be reclaimed? Yeah, it can be reclaimed, and it can look like that. But that doesn't happen overnight. If you get to the point where it looks like this, you've got several years before it's going to look like that, if you get it to that point. But unless you've got an outside source of water, okay, because you're going to have to leach those soils. But the other thing is you've got to get enough gypsum on there to actually get the sodium moved off out of the way and then do your leaching, okay? So it can be remediated, but it takes time. It's not a quick fix. The salt, once we get salts in the soils, it takes a long time to get them out, okay? So our recommendations: evaluate the soils and the drilling fluids first before you ever say, yeah, go ahead and put it out there. The drilling companies are supposed to have analysis, but again, they have analysis that meet the criteria for the regulations. We have some other things that we would like to see them analyze. And in Texas, sodium's a key, okay? And I think it would be here. I don't know whether it's required by Oklahoma or not. Will the soil be changed due to the salts and the clays in a detrimental way? I know money talks, And in Texas, they are offering anywhere from, what I've been told, anywhere from $10,000 to $30,000 an acre to land apply these materials. I know money talks, okay? But we have a legacy, we have a responsibility of our soils, okay? And so, is it going to cause a detrimental, any kind of detrimental effects? If it's land applied, don't put it on there over 3 inches. Disc it into the soil at least 6 inches. This is a big disc, okay? That's a 9-inch disc going into the ground, okay? It's not one of these that you pull with a little Ford tractor, okay? This is heavy duty equipment that you got to have to get it incorporated into the soil. This is a publication that we have through Texas that pretty much summarizes everything that I've talked about, that we recommend to the people in Texas. And so if that's something that you want to take a look at, it's there. Oklahoma State's got some good publications on their website as well. So, groundwater potential issues. If we've got a liquid that's injected back into a well, an injection well, you need to make for sure that those wells are that they are well cased and that they stay that way. Otherwise, that water can be released into some of the aquifers that we're getting, and we see that happening every once in a while on these injection wells. So just try to make for sure that that's not happening. From a standpoint of contamination from a surface water standpoint, there are some issues if we have any runoff from those materials that are not incorporated in a timely manner. And by timely manner, I mean that day or the next day, not 30 days later. Minimum analysis: pH, electrical conductivity, chloride, sodium, calcium, magnesium sulfate, sulfur, nitrogen, and then the TPH.